Thanks to everyone for coming to the talk. So the topic of this talk is kind of outlier of this session, more about regular expression, denial of service attacks. So my name is Tingjian. I'm from UMass Lowell. So this is a joint work with my collaborators from the Chinese Academy of Sciences. So unfortunately, they couldn't come. All right, so probably everyone knows about regular expressions. So regular expressions is very common in computer science. It's widely used in different areas, including network security, databases, programming languages, and so on. So we are talking about attacks. So this kind of attack is basically, a common problem with regular expression is to pattern matching, right? So given the input string, there are two types of matching. One is called full matching. So does the regular expression, fully match the input string or not? So the other type is partial matching. Does the regular expression appear at the substring of the input string or not? So for both variants, it's a challenging problem. It's either NL complete or NP complete, as is shown in previous work. So, however, in practice, this is not too bad. For many realistic input strings, it doesn't take too long. But we are talking about what kind of cases we may have a problem. Historically, there are two types of engines. One is based on the so-called backtracking engines. So namely, it can go back to a previous state and explore a different route to match the string. So this has been widely used in many programming languages and tools, including Python, Perl, and so on. Another one, more recent one, called non-backtracking. So basically means it doesn't go back to a previous state. It's more like automaton-based, like DFA or NFA, and so on. So this approach is considered to be more promising, safer, faster. And it's increasingly used in recent tools and programming languages. So we are particularly targeting this type of engines, non-backtracking engines. Some previous analysis showed that this is kind of linear, order n, where n is the size of the input string. But actually, there's some other analysis show that this is not entirely true. It also depends on, It also depends on the size of the regular expression. So once you expand the regular expression, so that's also another factor. Okay, so here's an example. So for this input regular expression, so this input string in the box, as you can see, many of the characters cannot be displayed. So this is going to be problematic. So we show that with non-backtracking engine, RE2, this is going to take almost 2 seconds. However, like Python's backtracking engine, this is not a problem. It only takes 1 millisecond. So this is just an example that shows that non-backtracking engine could be problematic for some strings. Although for other strings, it's better than backtracking engines. Okay, so this table shows some of our results. So our tool is called the Evo StringGen. So that's in 2 of the columns. So we're also comparing with another one called GetGCA. That's also a recent paper 2 years ago from this conference. They also target non-backtracking engines. So we saw example with different regular expressions. As you can see, our tool is able to generate strings that takes a significantly longer time than GetGCA can. And these are where it's vulnerable, right? This regular expression is vulnerable. It takes more than a few seconds. Okay, so GetGCA actually only targeting counting structure in the regular expression. That's one case of problem with non-backtracking engines. We also show that there are some other cases where this is a problem. So we analyze non-backtracking engines. So there's mostly based on DFA. So it's based on DFA state. And it also can go back to NFA if a DFA state has a problem. Sometimes it also go back to backtracking engines if both fails. So we look at the computational complexity of these measures and show that none of these are safe. So DFA state, as we see, the complexity, if you go to the worst case, it could be more than linear. Falling back to NFA is also not safe. So we also look at the so-called descriptional complexity. So this basically means that if you convert the regex expression to DFA, how many states do we have? So there are a few factors. One is so-called determinization blow up. So if you go from NFA to DFA, with many structures, including counting structures, we're going to have exponential size. Another factor is related to counting. So this is also analyzed in previous work, the GAT-GCA. Counting, including a nested counting, nested structures counting. So in our paper, we also find out there's another case with encoding. So with Unicode, if you go with UTF-8, which is variable length Unicode encoding, we often get many more states. So this table shows if you use ASCII encoding, there's no problem. Even for this simple example, /W/D, or repeat it 5 times and then finish. So, but with UTF-8, we're going to often get many more states, DFA states. So our next task is to try to come up with an attack, right? We come up with a tool algorithm to generate strings that's challenging for these type of engines. So to formulate this, we define the so-called simple string. So this basically means that this string, the intuition is that the string is going to explore many DFA states. Does not repeat, only goes through distinct states. So intuitively, this is a problem because the DFA engine had to generate many states, right, to match the input. So this is analogous to in graph theory, right? That's called there's a longest path problem. So between 2 nodes, what's the longest path? So that's known to be NP hard problem. So for our tool, we also want to generate some string like going through the path of the graph, where it does not repeat states, right? So that kind of corresponds to the longest path. So that's the intuition for a simple string. We also define a similar problem called K simple string. So it's a basic determination problem. So does there exist a simple string with length at least K or not? So we prove that in the paper, this problem is exponential space hard. So it's even harder than NP, okay? So given that, we try to come up with an algorithm with some heuristics that can generate challenging strings. So we based on 2 heuristics. One is so-called non-determined. So basically, we try to get to a state with more non-determinism. So intuitively, this means that it's going to be hard for the DFA engine because it needs to go through more states, and also the transition function will be hard. So that's one heuristic. So the other heuristic is called based on lexicographical order. So intuitively, this means that we want to get to a state that's far away from the finishing, the final states. Because once you get to the final states, right, the matching will succeed. So we during the on-the-fly DFA generation, we try to get to a state where it's far away from the finishing state. That's the second heuristics. So based on these 2 heuristics, so that's how our algorithm works. So yeah, I don't expect you to read the algorithm, but the basic idea is from these 2 heuristics. So if you're interested, you can read the paper for the algorithm. So now let's talk about some experiments. We did quite comprehensive evaluation. We used some well-known benchmarks with different regular expressions. And we also look at a number of engines, both backtracking engines and non-backtracking engines, although we mostly focus on non-backtracking engines. We compare with a number of baselines, including the GetGCA I just mentioned, and some other baselines. So in terms of metrics, we look at two types. One is called machine dependent, mostly about the running time, processing time for the input string. The other one called machine independent. So that's independent of the hardware, right? So mostly looking at the number of DFA states that it generates. So this table shows the main result. So the first 4 rows correspond to our tool called Evo String Gen. And we did an ablation study. So the 4th row is with all the options on, all the strategies on. We compare with a number of baselines. As you can see, we are able to generate strings very challenging, take significantly longer time than the baselines for both non-backtracking engines and backtracking engines. Although our work only target non-backtracking. So the other thing to note is one of the baseline, the last line, they did pretty well for Perl and PHP, slightly better than our tool, Evo String Gen. We also specifically compare with the previous work I mentioned, GetGCA, in the last table. As you can see, we also do much better than GetGCA. They only focus on counting structures. So this is a different view, scatter plot, just to compare with GetGCA. Our tool can generate string, takes much longer time and more states. We did some case study, a number of open source projects. So this one example is unknown/com. So we were able to find some problematic regex expressions, and that open project is widely used in other systems. So in summary, we find the problem with 85 projects and 34 regex expressions that's vulnerable. To summarize, for future work, we want to maximize the degree of non-determinant. Right now, we're using a greedy algorithm to increase the non-determinism. So we want to take a closer look. So in the paper, we also gave a number of suggestions to developers, like what kind of regex expressions to avoid. Right. Okay, thank you very much.